Welcome everyone, and thank you for joining me today. I'm excited to introduce our topic, phylogenetic diversity metrics in biodiversity. On this first slide, we're just setting the stage. We'll explore how, after calculating taxonomic diversity, we can push our analysis further by incorporating phylogenetic information. I'll also touch on a simple formula that links phylogeny and genetic data to cladistics with a timeline, showing how taxonomy and evolution come together. Over the course of this presentation, we'll dive into different metrics and methods to better understand the evolutionary relationships that shape biodiversity. So, let's get started and see how these concepts help us gain deeper insights into the natural world. Now, let's take a closer look at some of the key metrics used to measure phylogenetic diversity. First up is Faith's Phylogenetic Diversity, or PD. This metric essentially sums up the total branch length of a phylogenetic tree that connects all the species in a community. So, it gives us a sense of the overall evolutionary history contained within that community. Think of it as measuring the breadth of evolutionary heritage represented. Next, we have evolutionary distinctiveness, or ED. This one assigns a value to each species based on how unique its evolutionary history is. Species that have few close relatives, meaning they stand somewhat alone on the tree, score higher here. These species are particularly important because they represent a lot of unique evolutionary information. Then there's Rau's quadratic entropy. This metric is a bit more comprehensive because it considers not just the presence of different species, but also how abundant they are and how different they are from each other, either in terms of traits or evolutionary history. It's a way of capturing the overall diversity more holistically. Finally, we have phylogenetic endemism, or PE. This measures how evolutionarily distinct lineages are restricted to particular geographic areas. In other words, it highlights regions that harbor unique evolutionary histories that aren't found elsewhere. This can be especially useful for identifying conservation priorities. All these metrics help us understand the richness and uniqueness of biodiversity from different angles, which is vital for informing conservation strategies that preserve not just species, but the evolutionary processes that generated them. Now, let's take a closer look at this example tree structure. What you're seeing here is a visual representation of how data or information can be organized in a hierarchical way. At the top, we have the root node, which acts as the starting point or the main category. From there, it branches out into subcategories or child nodes, each representing a more specific aspect of the overall topic. This kind of structure is really useful because it helps us visualize relationships and dependencies between different parts of the data. It also makes it easier to navigate complex information by breaking it down into manageable sections. Throughout this presentation, we'll see how these tree structures form the backbone of many systems, from organizational charts to file directories and even decision-making processes. Understanding this example gives us a foundation for exploring how to design, analyze, and utilize these structures effectively. Now let's walk through how we calculate Faith's phylogenetic diversity, or PD, for the community consisting of species A and C. First, we look at the paths for each species. For species A, the path starts at the root, R, then goes through branch X, and finally reaches A. Similarly, for species C, the path is from R to branch Y, then down to C. It's important to note that the only shared branch between these two lineages is the root. There are no other branches they share, which means each species contributes unique evolutionary history beyond R. Next, we sum the lengths of all the branches involved in these paths. For the R to X branch, the length is 4 million years. The X to a branch adds another 1 million years. For C, the R to Y branch is 2 million years, and the Y to C branch is 2 million years. Adding all these up, the total PD for this community is 4 plus 1 plus 2 plus 2, which equals 9 million years. This total represents the entire evolutionary history that is unique to species A and C combined. One key point to remember is that we only include branches relevant to these species. For example, Branches leading to B or D, like X to B or Y to D, are excluded because B and D are not part of our community. So, in summary, Faith's PD captures the total amount of evolutionary history contained within our community. And in this case, it totals 9 million years, reflecting the distinct evolutionary paths of A and C. Now, let's take a closer look at how Faith's phylogenetic diversity, or PD, varies across different communities. First, consider the community consisting of species A and B. When we look at their shared evolutionary history, we see a subtree that connects R to X, which accounts for 4 million years, and then from X to each of A and B, which are 1 million years each. When we add these up, the total PD for this community comes to 6 million years. Next, look at the community with species C and D. Their subtree includes R to Y, which is 2 million years, and from Y to each of C and D, which are 2 and 3 million years respectively. Summing these branches gives us a PD of 7 million years. Finally, if we consider all 4 species together, A, B, C, and D, the total PD sums up all these branches, including the shared and unique parts. That adds up to 13 million years. What this all shows us is that Faith's PD isn't just about counting species. It's about measuring the total amount of evolutionary history contained within a community. It captures both shared evolutionary branches and unique ones, giving us a richer understanding of biodiversity, what we often call evolutionary richness. This helps us appreciate not just how many species there are, but how deeply interconnected and diverse their evolutionary backgrounds truly are. Now, let's take a closer look at how we calculate evolutionary distinctiveness, or ED, for each species based on their position in the phylogenetic tree. The tree shows the relationships and branch lengths connecting these species, and those branch lengths represent evolutionary time or change. To determine ED, we use what's called the fair proportion method. Essentially, this means we look at each branch from the root of the tree all the way down to the species, and we assign a share of that branch's length based on how many descendants it has. So, if a branch leads to 2 species, that branch's length is split between them. If it leads to just one, that species gets the full length. For example, look at species A. It shares the initial branch from the root, R, to X, which is 4 units long. With B, since both A and B descend from that branch, we divide the length equally, so each gets 2. Then, from X to A, there's a 1-unit branch unique to A, so A gets the full one there. Adding those up, A's ED totals 3. Similarly, for species B, the calculation is the same. The shared branch contributes 2, and the branch to B adds 1, totaling 3 as well. Now, for species C, the initial branch from R to Y is 2 units, shared with D, so each gets 1. From Y to C, there's a 2-unit branch unique to C, so C's ED sums to 3. For species D, the same shared initial branch gives 1, but from Y to D, there's a longer 3-unit branch that D alone has. So D's ED is 1 plus 3, totaling 4, which is the highest among these species. This indicates that D has the most unique evolutionary history, mainly due to its long, solitary branch. Overall, this method helps us quantify how much unique evolutionary heritage each species carries, which is crucial for prioritizing conservation efforts and understanding biodiversity. Now, let's walk through how we calculate Rao's quadratic entropy, or Rao's Q. This measure considers not just how many species are present, but also how related they are phylogenetically, as well as their relative abundances. Essentially, it captures the diversity in a community by combining evolutionary distances with species abundance data. First, the formula involves summing over all pairs of species, where dig represents the phylogenetic distance between species I and J, and pi and pj are their relative abundances. The key assumption here is that our community contains species A, B, and C, with species D absent. The abundances are given. A and B each have 1 individual, and C has 2, making a total of 4 individuals. From those abundances, we can calculate the relative abundances. A is 0.25, B is 0.25, and C is 0.5. Next, we consider the phylogenetic distances. Between A and B, the distance is 2, which is the sum of the branch lengths connecting them through an intermediate node. Between A and C, the distance is 9, reflecting a more distant evolutionary relationship. Similarly, B and C also have a distance of 9. Now, when we perform the calculation, we sum over all pairs, including the pairs where I equals J, which have a distance of 0. So, for example, DAA is 0, as is DBB and DCC. The formula involves multiplying the phylogenetic distance by the product of the relative abundances for each pair. Putting it all together, the calculation looks like this. We multiply each distance by the corresponding abundance products, then sum everything. When we do the math, the total Rouse Q comes out to 4.75. This value indicates the overall phylogenetic diversity in this community. Notably, it's higher than it would be if the species were more closely related or clustered phylogenetically, which makes sense because the distances between A and B versus C are quite large. So, by incorporating both evolutionary relationships and abundances, Rouse quadratic entropy provides a nuanced measure of community diversity that reflects both the variety of species and their evolutionary history. Now, let's walk through how we calculate phylogenetic endemism, or PE, which essentially measures how much evolutionary history is unique to a specific geographic region. To do this, we start by enhancing our phylogenetic tree with range data for each species. In our example, Region 1 contains species A and B, both endemic to that area, while Region 2 has species C and D, also endemic. The core of the PE calculation involves summing the branch lengths, but we weight each branch according to how restricted its range is, that is, how many regions it appears in. The formula we use is PE equals the sum over all branches of the branch length multiplied by the range restriction weight. And this weight is calculated as 1 divided by the number of regions the branch is present in. So, if a branch is only in one region, its weight is 1. If it appears in multiple regions, the weight decreases accordingly. Let's look at step 1, identifying the branches and their geographic presence. For example, the branch from the root to species A and B, called R to X, is only in region 1, so its weight is 1 divided by 1, which is 1. Similarly, for the branches leading to each species, since they are endemic, their range restriction weights are also 1. Moving to step 2, calculating PE for each region. For region 1, we sum the branch lengths, multiplying each by its corresponding weight, and get a total PE of 6. For region 2, the sum is higher at 7, mainly because it has longer unique branches in its subtree. This difference indicates that region 2 holds slightly more unique evolutionary history, which is reflected in its higher PE value. So, in essence, PE helps us quantify how much evolutionary heritage is confined to each region, highlighting areas that harbor unique lineages. Now, let's take a closer look at some key insights we can gain from phylogenetic diversity metrics. First, we have evolutionary distinctiveness, or ED. This metric helps us identify species that are evolutionarily unique, particularly those with few close relatives. For example, a species like D scores very high, with an ED of 4, indicating it's quite isolated on the evolutionary tree. Such species are often top priorities for conservation, because losing them would mean losing a significant chunk of evolutionary history. Think about pandas or tuataras. Next, we have Rouse quadratic entropy, which brings together how abundant species are and how distantly related they are. Basically, it tells us about the overall phylogenetic diversity within a community. When communities contain species that are distantly related, Rouse Q value is higher, suggesting greater functional diversity. This insight helps us guide habitat protection efforts. By focusing on areas where such diverse communities exist, we can support ecosystems with more functional resilience. Finally, we look at phylogenetic endemism, or PE. This metric helps us pinpoint regions that harbor unique evolutionary history that's geographically restricted. For example, Region 2 might contain deep, unique branches of the tree of life, making it a hotspot of endemicity. These regions are crucial for reserve design and conservation planning because protecting them means safeguarding irreplaceable evolutionary heritage. To sum up, these metrics, ED, ROUSE-Q, and PE offer complementary insights. ED highlights species that are evolutionarily unique. ROUSE-Q provides a community-level perspective on diversity, and PE points us toward regions with concentrated, restricted evolutionary history. Together, they give us a well-rounded view of biodiversity that's essential for effective conservation strategies.